Dear students, in this video I am going to discuss numerical problems appeared in the year July 2017. Watch full video that helps you to score more in the upcoming examinations. So let's have a look on the very first problem, that is, in a parallel plate capacitor with air between the plates, each plate has an area that is 8 into 10 raised to minus 3 meter square. That is, area of the plate A equals to 8 into 10 raised to minus 3 meter square, and distance between the plates is 2 millimeter. That is, distance between the plate equals to 2 millimeter. That is, milli means 10 to the power minus 3 meter. Calculate the capacitance of the capacitor. If this capacitor is connected to 50 volt supply, that is V equals to 50 volt supply, what is the charge on each plate of the capacitor? We have here absolute permittivity of the free space, that is epsilon naught. We have 8.85 into 10 raised to minus 12 force per meter. So we need to calculate capacitance of the capacitor, that is C, and if this capacitor is connected to 50 volt supply, what is the charge on each plate of the capacitor? So we need to calculate charge on each plate of the capacitor when it is connected to a 50 volt supply. So now we know that a relationship between, or an expression for the capacitance of the parallel plate capacitor, that is C equals to epsilon naught A divided by D. Substitute the values, that is epsilon naught equals to 8.85 into 10 raised to minus 12 into area of cross section 8 into 10 raised to minus 3 divided by D, that is 2 into 10 raised to minus 3. 10 to the power minus 3, 10 to the power minus 3 get cancels, and 2 1 ja, 2 4 ja. So we get the capacitance of the parallel plate capacitor is equal to the 35.4 into 10 raised to minus 12 farad. So this is what capacitance of the parallel plate capacitor. C equals to 35.4 into 10 raised to minus 12 farad. Now we need to find out one more factor, that is a charge on each plate of the capacitor when it is connected to 50 volt supply. So we know that the charge on each plate of the capacitor is equals to the capacitance times the voltage supplied across its ends. That is, the capacitance equals to 35.4 into 10 raised to minus 12, and the voltage, that is 50 volt here. So if you simplify, you will get the charge is equals to, that is 1770 into 10 raised to minus 12 coulomb, and this can be written as, that is Q equals to 1.77 into 10 raised to minus 9 coulomb. That is nothing but Q equals to 1.77 nanocoulomb. The charge on each plate of the capacitor when it is connected to the 50 volt supply is 1.77 nanocoulomb. Okay, let's move to the next question, that is, 3 resistors 4 ohm, 6 ohm and 8 ohm are connected in parallel. What is the total resistance of the combination? Here we have 3 resistors. Let me name them as R1, R2 and R3. Here R1 equals to 4 ohm, R2 equals to 6 ohm and R3 equals to 8 ohm. They are connected in parallel. Whenever resistances, 3 resistances connected in parallel, their effective resistance can be calculated by using the formula 1 by Rp. That is, Rp is the effective resistance of the combination. 1 by Rp equals to 1 by R1 plus 1 by R2 plus 1 by R3. Substitute the given value, that is 1 by 4 plus R2 is 6, R3 is 8. So take LCM, we get 24, and here 6 plus 4 plus 3. So we will get 13 divided by 24. This is 1 by Rp. So but we want Rp, that is effective resistance of the three resistors when they are connected in parallel. That is 1 by Rp equals to 24 divided by 13. This will be equals to 1 by Rp equals to, that is 1.8461. So this nearly equals to, that is Rp equals to 1.85 ohm. This is the effective resistance of the combination. This is question A. Now let me move to the B. If the combination is connected to a battery of EMF 25 volt and negligible internal resistance, determine the current through each resistor. Here we have EMF, that is EMF equals to 25 volt and internal resistance is negligible, that is equals to 0. Now current through the circuit is given by the expression, that is I equals to E divided by resistance, external resistance plus internal resistance. Now let us find out the current through each resistor. That is, let me consider the current through R1 can be written as I1. That is, I1 is equals to E divided by R1 plus R. Here let me substitute the value, that is E equals to 25 volt divided by R1 is 4 ohm plus 0, and this is equals to I1 equals to, so 6.25. This is 6.25 ampere. This is I1. Next, let me find out I2 in the same way. That is, I2 is equals to E divided by R2 plus R. Substituting the values, we get E equals to 25, R2 equals to 6, and this is equals to, so that is 4.166. This is I2. In the same way, we can find out I3. That is, I3 equals to E divided by R3 plus R. So I3 equals to E 25 volt divided by R3 is 8 ohm plus 0. This could be written as I3 is equals to 3.125 ampere. That is current through each resistor. We found that I1, I2, I3 are the currents which are flowing through the resistors R1, R2 and R3 respectively. Now, so we need to find out the total current drawn from the battery. Total current drawn from the battery can be written as I equals to E divided by RP, that is E divided by RP plus R. As you know that E is 25 volt and RP is 1.85 and this is 0, that is internal resistance is 0. 25 divided by 1.85, 25 divided by 1.85, that is equals to 13.5 ampere. This is the total current drawn from the battery. This you can get by adding I1, I2 and I3 also. So we can you can use I equals to E divided by RP plus R, or else just we can add I1 plus I2 plus I3. This is the total current drawn from the battery. Okay, let's move to the next question. That is, a sinusoidal voltage of peak value 285 volt is applied to a series LCR circuit in which resistor of resistance 5 ohm, pure inductor of inductance 28.5 millihenry and capacitor of capacitance 800 microfarad are connected. Find the resonant frequency and calculate the impedance, current and power dissipated at resonance. So let's find out first resonant frequency. For this, let me write first the given data here. that is peak value of the sinusoidal voltage, that is sinusoidal voltage of peak value, that is V naught. We have here V naught equals to 285, that is peak voltage is V naught, and is applied to a series LCR circuit, and resistance, that is R is equals to 5 ohm, inductor of inductance, that is L equals to 28.5 millihenry, that is milli means 10 to the power minus 3 Henry, and capacitor of capacitance, that is C equals to 800 microfarad are connected. Find the resonant frequency. We have an expression for resonant frequency, that is we have a formula, that is F is equals to resonant frequency equals to 1 divided by 2 pi square root of LC. Okay, substitute the values now, that is 1 divided by 2, pi value is 3.142, square root of LC, L is equals to 28.5 into 10 raised to minus 3 into C equals to 800 into 10 raised to minus 6. So when we simplify, we get F is equals to 1 divided by 2 into 3.142, that is 6.284 square root of 22,800 into 10 raised to, here 10 to the power minus 3, 10 to the power minus 6, 10 to the power minus 9 we will get. This can be written as 1 divided by 6.284 square root of, so here you may get even number by taking like this, that is 2280 into 10 raised to minus 8. We could write like this also. This will become 2280. Now, applying square root, we can get 1 divided by 6.284 here, square root of 2280, that is equals to 47, it is 47.75 into 10 raised to minus 14, and this is equals to 10 to the power of minus 4. If it goes up, it will become 10 to the power of plus 4 divided by 6.284 into 47.73. This is equals to 6.284 into 47.75. This is equals to 300. Now, simplifying, we get, that is 10 to the power of 4 is nothing but 10,000. This can be written as 10,000 divided by 300, that is this 2020 get cancelled, so we will get 100 divided by 3 is nothing but 33.33 hertz. This is the resonant frequency. F is equals to this much. Now find the resonant frequency, and let me say B. Calculate the impedance, current and power dissipated at resonance. At resonance we need to find out. So as we know that at resonance, we have seen that XL is equals to XC as well as Z is equals to R. So we could write here Z is equals to the R value. So here R value is 5 ohm, that we can write here R equals to 5. This is what impedance. At resonance we can write XL equals to XC. At resonance XL equals to XC. So Z equals to R. Now Z equals to 5. So how can we get this? Because we know that impedance is equals to square root of R square plus XL minus XC whole square. If XC is equals to XL, then the square root of R square becomes R. So we could write Z equals to R. So we have impedance 5. Next, we need to find out the current. So current is equals to, that is at resonance the current is maximum. So we could write here the I naught, that is maximum current, is equals to, that is V naught divided by Z. So here we have V naught is equals to 285, that is 285 divided by 5. 285 divided by 5. This is equals to, that is 285 divided by 5 is equals to 57 ampere. That is I naught. Now we need to find out power dissipated. Let's see now the power dissipated at the resonance. Power dissipated is used to, as we know that power equals to VI, that is peak voltage and peak current. So V naught is equals to, we have seen that V naught here 285 and I naught equals to 57. So this power dissipated. So power dissipated in the circuit is equals to 16.245. This is what the B. So we calculated resonant frequency as well as impedance, current, power dissipated in the dissipated at resonance. Okay, so let's move to the next question. That is, in Young's double slit experiment, distance between the slits is 0.5 millimeter. When the screen is kept at a distance of 100 centimeter from the slits, the distance of the ninth bright fringe from the center of the fringe system is 8.835 millimeter. Find the wavelength of the light used. Let me write first given data. In Young's double slit experiment, the distance between the slits is represented by the letter small d, that is given here, that is small d equals to 0.5 millimeter. Milli means 10 to the power minus 3 meter. When the screen is kept at a distance, that is the distance between the screen and the slit, that we know, that is capital D, equals to 100 centimeter. 100 centimeter is nothing but 1 meter. From the slits, the distance of the ninth bright fringe, that is N ninth, distance of the ninth bright fringe from the center fringe system is 8.835, that is distance of the ninth bright fringe from the central fringe is equals to 8.835 millimeter. Milli means 10 raised to minus 3 meter. Find the wavelength of the light used. We need to find out wavelength of the light used in this experiment. As we know that the distance of the nth bright fringe, let me write distance of the nth bright fringe from the central fringe is given by, that is xn is equals to n lambda d divided by d. This is the expression for the distance of the nth bright fringe from the central fringe. Just we have seen that x to the power of xn is equals to n lambda d divided by d. We have make lambda as a subject formula now to get wavelength of the light used. So we will get now lambda is equals to xn into d divided by n into capital D. Now on substituting the values, we get lambda equals to xn. Here we have xn is equals to, that is distance of the ninth bright fringe. We are having here ninth bright fringe, d divided by n into capital D. Now let me write distance of the ninth bright fringe from the central fringe is 8.835 into 10 raised to minus 3 into distance between the slits, that is 0.5 into 10 raised to minus 3 divided by n. N is ninth bright fringe and distance between the slits and the screen is 1 meter. So on simplifying, we get lambda is equals to 8.835 into 0.5, which gives us 4.4175 into 10 raised to minus 3, 10 raised to minus 3, it will become 10 to the power of minus 6 divided by 9. Now lambda equals to, Calculating, we get lambda is equals to 0.4908 into 10 raised to minus 6. Now let me move the decimal point to here. So we get now 4908 into 10 raised to minus 10. That is lambda equals to 4908 angstrom. Okay, this is the wavelength of the light used in this experiment. Okay, let's move to the next question, that is calculate the binding energy and binding energy per nucleon of an oxygen nucleus using the following data. Mass of proton is 1 point. Let me write here first. Mass of the proton, that is mass of the proton is equals to 1.007825 U, and mass of the neutron, let me write mass of the neutron equals to 1.008665 U, and mass of the oxygen nucleus, that is mass of the nucleus equals to 15.995 U. So here we have the mass number equals to 16 and atomic number equals to 8 for the oxygen nucleus. Now we need to find out binding energy. To find out binding energy, we must write the relation between the binding energy and mass defect, because we need to express the binding energy in terms of mega electron volt. So we can have a relation between binding energy and mass defect, that is binding energy is equals to mass defect times the 931.5 mega electron volt. This is the relationship between mass defect and binding energy. Now this can be written as, that is mass defect is given by Z mass of the proton plus mass of the neutron, that is total number of neutrons, A minus Z into mass of each neutron, let me write, minus mass of the nucleus, that is actual mass of the nucleus. This is the formula for mass defect, into, that is 931.5 mega electron volt. Now substituting the values, that is here Z equals to 8, the mass of the proton is 1.007825 plus A minus Z, that is 8, into mass of neutron is 1.008665, and mass of the nucleus, actual mass of the nucleus is 15.995 times, that is 931.5 mega electron volt. I'm simplifying this, we get binding energy, that is binding energy is equals to, let me write here, binding energy equals to 8 into 1.007825, that is equals to 8.0626 plus, and 8 into 1.008665 is equals to 8.06932 minus 15.995 into 931.5 mega electron volt. Now this can be written as, that is if you add all this, we will get 0.13692 into 931.5 mega electron volt, and this is equals to, that is binding energy equals to 127.54 mega electron volt, 54 mega electron volt. This is the binding energy of the oxygen nucleus. Now we need to find out one more parameter, that is binding energy per nucleon. Binding energy per nucleon is also called as specific binding energy, that is binding energy per nucleon. Binding energy per nucleon is also called as specific binding energy, and this can be written as binding energy by mass number. So binding energy just now we got, that is 127.54, 127.54 mega electron volt divided by the mass number is 16, that is 127.54 divided by 16. We get 7.97 mega electron volt. This is binding energy per nucleon, that is Be divided by A. Okay. Binding energy per nucleon is 7.97 mega electron volt, and only binding energy is 127.54. Okay, this is the answer. Okay, thank you. Thanks for watching.